Hello, this is Dr. Asan Abdullah with the course Deep Reinforcement Learning, which consists of several topics. And one of the important topics is convolutional neural networks. And this is the seventh topic in the list of topics. And the subtopic is C, so of moderate difficulty level. So this lecture is 7C. And this uses the supplemental website, which is available at www.ezmcq.com/GoGet, which is a personalized learning management system based upon content delivery, and the features of that content delivery are listed on your screen. And this is ahead of the traditional slides based approach, and this approach is literally used by hundreds of millions of online users throughout the world. And based upon that content delivery, we have developed the personalized learning management system. In green color is the URL of the personalized learning management system, and it consists of several features. The key six features are shown and demonstrated in six videos. The URL of those videos is shown on the screen in blue color. So, what are those features? For example, full text search in the content of all the questions and answers, and ability to support people having handicap or disability or some limitation of viewing, so they can send or set the color, size of the font, spacing, and so on. And it optimizes the limited space of the smart handheld devices in a hierarchy of the content. And of course, you can also track your progress so that you know what you have done and what you need to do. And there is the facility of online testing and grading and evaluation of results. And of course, this is centered around the question and answer based approach, which is engaging, which is thought provoking, which is very powerful, which is proactive also, and the details of the traditional approach. So it's the best of both worlds, and it is a blending of these two technologies and techniques. So in front of you is the list of topics which are covered in this course, and we are at topic number 7. That topic is convolutional neural networks, and the contents of this topic are on your screen now. Every question and answer is a concept. So those concepts are divided into groups. So the lecture number 7A grouping is shown in yellow color, and the next grouping in green color, and so on. So the difficulty from yellow to purple increases progressively. Now, without further ado, now we move on towards the actual lecture. So we start with deep learning video 7C. So what are the examples of more popular CNN architectures? Now, it's not that there is a single or one or two CNN architecture. There are quite a few CNN architectures. Some are more influential than the others, and which have led progress in deep learning. Now, there is the LeNet 5 architecture, which is core CNN concept like convolutions and pooling for digit recognition, not images. Then is the AlexNet, which brought deep learning into the mainstream, into the spotlight by winning the ImageNet 2012 challenge. That ImageNet we have discussed. Then there is the VGG networks that emphasize deeper architecture using consistent 3 by 3 filters. So this is how it is implemented, and which shows significant improvement in accuracy, of course, at a high computational cost. Then is the GoogleNet Inception, which that uses parallel convolutional paths. Then is the ResNet, and so on. So what do these models do? These models have laid the foundation for modern convolutional neural networks, and at the same time improving feature learning, scalability. So they scale with the increase in the problem size, and accuracy also in both computer vision and reinforcement learning. So if we look at here, so in terms of gigaflops, in terms of accuracy, we can see that the leader here is NASNet-A. This is the leader. And in terms of volume, it is not the leader in terms of volume, but overall in terms of the accuracy and operations. And you can see that this is a specific class VGG. Okay, so this is a class of its own. So we will briefly go over them, and but these are kind of proprietary. So what we intend to cover these are the features. Okay. So LeNet was for hand written digits, and that we've discussed. So VGGNet, which has a class of its own, they are stacked uniform. They are stacked uniform convolutions for deeper networks. You can read it from here. I don't have to read it for you. Okay. And so this is how these are the leaders, and the more details are given here. And if you are interested, you can read the references. So now we move on to the next Q&A, which is which problems of fully connected neural networks CNNs were able to overcome. Of course, fully connected networks require more hardware, they require more processing power, they need more energy consumption, they have more energy consumption also. So CNNs are not just popular because of novelty, but they have been able to uh, overcome the problem of FCNs or fully connected networks. Now these FCNs face several challenges when processing visual data. So how does CNN overcome these problems? By introducing local connectivity and by using shared parameters. So what it translates into reduction in the computational complexity and the reduction in the number of trainable weights also. What it does that it for FCNs that results in overfitting, but in CNNs this overfitting is reduced. Now FCNs also ignore the input structure, while CNNs build spatial hierarchies, and in this process they learn the localized features, for example like edges or textures, and they gradually combine them into more complex patterns as we go further downstream in CNN. They also offer translational invariance that I've mentioned a number of times. Okay, and what it does, it improves the robustness, which I've shown you through the max and through the average also. And last but not the least, CNN scale efficiently to higher resolution input. And that's where, when the resolution increases, FCNs becomes computationally prohibitive, taking a lot of time, requiring a lot of hardware, lot of energy. Okay, so that's this how CNNs are able to work for with more uh, large and spatial data. So here we have this diagram we've already covered a number of times, right? So this is the of a CNN semantic representation. So we have a single convolutional layer and two hidden layers of fully connected nodes. These are the fully connected nodes, and the flattened layer also, and a softmax function. So let's cover this, and what we will be covering here is the high computational cost, which is the problem with FCN, and due to sharing of parameters resulting in overfitting, another problem of FCN. FCN means fully connected network. A lack of spatial hierarchical feature extraction, it's not there. This helps in image recognition. Inefficient parameter sharing, very little parameter sharing, and difficulty in handling variation in the input data, which we have covered is not an issue with CNN in the previous Q&A, and the scalability issue because that's fully connected. So these are the details which we'll be covering here. So let's jump into those details. So high computational complexity. Now fully connected networks require one weight per connection. Therefore, millions of parameters for image inputs. Obviously, this results in heavy computation cost, energy, and slow training. Now, CNNs reduce the complexity by using those filters and sparse connections, which significantly lower the number of operations, while it still captures the essential spatial features in the data. Essential features are captured, right? But unnecessary details, they are kind of dropped out. Okay. Now, for FCN, a fully connected network, overfitting is an issue. Why? Because large number of parameters. If you look at all the details, then say for example, a child is not able to recognize his or her mother, okay, with a slight change in the makeup, large number of parameters. Usually the child is used to recognize and seeing his her mother without makeup, large number of parameters. That is an overfitting. Now the dense character of fully connected layers can lead to overfitting, especially when limited training data. Why? Because it starts memorizing, and the issue is excessive number of parameters. Now, how what the CNNs do is mitigate this by using shared weights through the convolutional filters. I'm sorry, and reduce the number of parameter count. Okay. So what is the result? The result is improvement in generalization. How? By focusing on local patterns rather than memorizing the training set, which I've already discussed. Then is lack of spatial hierarchical feature extraction. There in FCN there is no hierarchy. They just flatten the input data. So the spatial arrangement of pixels is lost. So as a result, the FCN lose their ability to understand spatial hierarchies like edges, like textures, like shapes, etc. However, CNNs preserve the spatial structure. How? Through layers of convolutional and polling. What and how it helps? Allowing them to progressively learn complex hierarchical visual features. Why they are important? They are crucial for understanding the images. All right. Inefficient parameter sharing. Fully connected neural networks, okay, uh, have their own issues, like unique weight for every connection. So there is no sharing of, as a matter of fact, it's impossible. Sharing of parameters is impossible. Therefore, the training is inefficient. As opposed to CNNs use filters that slide across the input image, which I've shown you, and applying the same weights to different regions, as opposed to different weights for FCN. Now, this efficient reuse of weights significantly reduces the requirement of memory, reduction in the computational cost. The beauty is without sacrificing the representational power of the model, and consequently without reduction in accuracy. Now, FCNs have difficulty in handling variations in input data. Okay, they like kind of struggle to generalize over the transformations like the translation, the scale, the rotation in the input image or images. Why? Because they treat all inputs and all features equally, which is not the case in real life. So what CNN does, it handles such variations better using convolution and pooling operations. This naturally provides some degree of translation invariance, which makes them robust to what? To different visual appearances. And finally, the scalability issues. Okay, as the network size increases, FC and a fully connected network scale poorly because the increase is quadratic. The linear increase in input size results in a quadratic increase in the complexity of the network. Okay, why? Because of the exponential growth in, and then the parameters grow exponentially, and the memory requirement grows exponentially. Now, these are not the issues with CNN. Why? Because they address this with local connectivity and weight sharing. Thus, CNNs are like far more scalable as compared to FCNs for high dimensional inputs like large images or large long videos. At the same time, maintaining the performance and managing the resource usage. That's the beauty of it. All right. So the details are here. Okay. The problem with fully connected neural nets, FCNNs, and convolutional neural networks, and the references are here. Okay. So now we move on to the next Q&A or the concept. Okay, now we are at the next Q&A or the concept. So kind of a hands-on type. So how to set up a baseline linear classifier for images of size 20 by 20. Now 20 by 20 image is going to be very small, fairly small, and we will be working with character 3. So before we go ahead, so basically these are the steps. So we are working with character 3, right? So flatten the input and then normalize pixel values, and the details are given in the form of bullets. So train with loss. Loss means that of course when you kind of lose the data, there is a loss, and that loss of data basically has to be critical because this can affect the prediction also. So before we go into the detail, a little bit of background. So to set up a baseline linear classifier for 20 by 20 grayscale images, what we need to do is, first of all, each image is flattened into a 400 dimensional vector. So this is the image 20 by 20, and this is flattened into a 400 dimensional vector. So it's a vector, right? Pixel values are then normalized. Normalized being that they are adjusted between 0 and 1 value. So this has certain pixel values. Of course, they are not 0 and 1. Why we do this? Because it helps to standardize the input and makes the training stable. Then what we do next is that we use a weight matrix which is initialized with one row per class and one column per pixel. So for example, if you have 10 classes, it's a 10 by 400 weight matrix, right? Now all of the stuff which I'm talking about is not drawn here, and a BICE term is also included for each class. So class scores are computed through a dot product which we have already discussed, and that dot product is between input vectors and class weights plus the bias. Now what happens is that these scores are passed through a softmax function. What that softmax function does is produce the probabilities for multi-class classification. Now it may sound a little technical, so therefore I would strongly suggest you that you read the following material. Okay, what is the following material? This is the material I'm talking about. So I would strongly urge you to read this material. I am giving you brief details of that material, and if you are further interested, here are the references which were used to prepare this. So now the scores which I was mentioning, these scores are passed through a softmax function that produces the probability for a multi-class classification. So the model is trained using a cross entropy loss function. There are different types of loss functions, and weights are updated via gradient descent or a variant. And we have extensively, as a matter of fact, there is a complete topic on gradient descent. So what happens during inference? The model outputs probability for each class, that it's a 3 or a 4 or a 5, whatever, and selects the highest scoring class. So maybe it correctly selects 3, or maybe it incorrectly selects 8 or something else. Now this method serves as a simple yet effective baseline for image classification. Okay, so if you go into the details, so what happens when we perform this task? Flatten the input. What happens that if we convert each 20 by 20 image into a single vector of size 400 values, because then it makes it usable for mathematical operations in the model and for our computations. Because until and unless there is a mathematical representation of a process or something, if something cannot be represented using a model, it's very difficult to have mathematical operations on it. So after we're done with this, then what we do is normalize the pixel values. Now, because the pixel values are varying, so to make them consistent, scale all pixel values to a 0-1 range. So then it ensures stability and consistent feature influence. Otherwise, the pixels which are dark, as we can see in this image, they can have more profound impact as compared to the white pictures. and the pictures which are for aliasing is the border, making it a shade of gray for a smooth change. So that would be have a different influence. Then what we do is that we define a weight matrix. So what is a weight matrix? We have covered this when we started CNN. So we initialize a 10 by 400 matrix, right? 10 by 400 matrix. So there are 400 columns and there are 10 rows or 10 values. To map each image's 400 features to the 10 output classes. So we have 10 classes like 3, 0 to 9. We have 10 classes and we assign the weights for that weight matrix. That's how it's working. Compute the class scores. So once we have done this, then we use a dot product and we use and add the bias to calculate the class scores for each of the 0 to 9 handwritten characters and determine the highest score as per the prediction. Determine the highest score. So number 5 is train with loss. Minimize the classification error. How? By using cross entropy loss. And update the weights using gradient descent so as to reduce the error. Right? So using gradient descent, you kind of update the weights so to reduce the loss or the error. All right. Then what is done next? Evaluate and predict. All right. So run the trained model on the new unseen data. Maybe there are almost infinite ways of handwriting 3. So there is another set of letters or classes handwritten. So run the trained model on the new data to predict the most probable class and evaluate performance using the metrics. That how accurate your training is how accurate is the training of the model. All right.